No. Minimize.
Cancel. Good.
Okay. So welcome back to our class now. So in the morning session, we already done with the EMI. That is a theory part of the EMI. Now in this session, we will do some questions on EMI, and after that, we, according to the time, we can continue our AC topics. So already we prepared some questions, which is frequently asked questions. So we will see that question and how to deal with the questions. In that one, few MCQ question is there, few assertion reason question is there, and few simple numericals which can come in this topic. That's also there. So we will see the questions. What are the types of question which can come from this topic, and what are the types of question which previously came from this topic. So we will start with a question. Okay, so we'll start with this question. Actually, you can see the question, I think. So we have a special situation mentioned here. So in this situation, whenever you are seeing this one like this, people will leave the question. What they don't know what to do, and they will feel it is something which we cannot understand. So that's why first itself I took such a question. Actually, this is based on the concepts which you know, and entire thing you know. Actually, because of the fear of this vector notation, many people used to leave such question. So that's why we are first dealing such a question. So you see here, the question says a square of side L meters. That is a square, so all the sides will be L in L meters, lies in the XY plane in a region where the magnetic field is given by B is equal to B naught 2I plus 3J plus 4K Tesla, where B naught is a constant. The magnitude of the flux passing through the square is, just you have to calculate the flux. So what we have to calculate is phi B. So we have to calculate phi B, or the magnetic flux. Magnetic flux is B dot A, we know. So here actually 4 values are given. So we should take which is the actual answer for this one. This is an MCQ question type. Already answers are given. So in this one, we have to first analyze the situation here. So it's already given a square is there, which is L meter, which is in the XY plane. So what is this meaning of that one? It is in the XY plane. If you draw the plane like this, let it be X axis, this is Y axis, and this is Z axis. Okay. So to take this plane, I taken this X as that side and Y as this side. So this XY plane means our loop is like this. So this side is L, this side is L. So it is in the XY plane. That's what it says. Now, and given by magnetic field is given by this one. So we have a magnetic field here. Now, what we have to do is we have to find out this B dot A. So how to find out this one? So that's what. So if this area is in the XY plane, here when you are taking B dot A, this is a vector. B is a vector and area is also a vector. So the most important thing is here we have to find out the direction of this area vector. So as the area is like this, the area vector will be like this. A will be along that direction. That's the most important thing here. The direction of area vector is along this Z axis, or it will be along K. So this, you know that this is I is along this side, and J is along this side, and K is along. So our point is the area will be along the vector K. That's the most important thing. So what is the magnitude of area? Already given. The length is L. So it is a area like this. Square. This side is L. This side is L. So it will be L square. And it is along this direction. That is most important thing. So it will be L square K. So this is the area. So if you get that area, our problem solved. So here, once more, you read this one. A square of side L meters lies in the XY plane. So it will be X is this way, Y is this way. So that this is our area. So first thing is the physical area is like this, but the direction of area vector is along this direction. That's what first we have to do. So the area vector is along this direction. So L is one side, means L square will be the area, and the direction is along K. So L square K is the area here. Now the second part is easy. Just I will show the solution of this one, so it will be easy for you. So the explanation is here. The magnetic flux is defined as the total number of magnetic field lines of force passing normally through an area placed in the magnetic field, and is equal to the magnetic flux linked with the area. So the normal thing is given. So what we told, the area is given by this one. This is what we done just now. Area is equal to L square K. Now what is the flux? This is flux phi is given by phi B is given by B dot A. So B is already given in the question. B is B naught into 2I plus 3J plus 4K. This is already given in the question. Dot area. So this is our B and this is our area. Area is L square into K. So when you are taking the dot product, you know, you are the corresponding thing you have to multiply. So when B naught will be here, and this, when you are taking only K is there, so that only K will remain there. When you take the dot product, you can see here this I and J, that will become 0, only that K thing will be remaining there. So this one, when you take the dot product, you will get like this. So this is our answer. This Weber is the unit. So for B naught L square, you will get this 4 is from this one, and this L square is already there. Okay, so for B naught into L square, you will get. So this option is there in the previous one. This one, I think this one. The option C is the correct answer for this one. Okay, so once more, for those who not understood what to do, once more I will tell this one. First, you have to find where is the area. So after this area, you have to find out what is the direction of area. Sometimes it can be in the opposite way. This magnetic field also can be in a single direction. That also you can take. Sometimes here it's I, J, both will be 0, along a particular direction will be there. But whatever be the case, you have to analyze in which direction is the magnetic field, which direction is the area, like that. So here we got that area as L square K and magnetic field is like this. Just you take the dot product. You already done in 11th standard, so you can get the dot product, and option C you will get as the correct answer. I think so most of the people might have understood this one. If you have any difficulty, you can practice 1 or 2 more questions the same way. So this is a question which we can expect. Okay, this type of question. And most of the people, as I told, this one, when you are getting this vector notation, people will leave it. We cannot do it like that. It's not like that. Vector notation also everybody can do. So you should be confident that this one we done previously, so that we can do this type of question also. So in the beginning itself, I had done such a question, and afterwards we have simple question also, because whenever you are getting a question paper, you will have all type of question. This type of question will be there, and simple direct question will be there. Everything will be there. So next you will see a simple direct type question. Okay, so this one is another question from the same EMI chapter itself. See here, you read the question. The polarity of induced EMF is defined by simple only. Already we done the polarity, that is we done that EMF is given by minus d phi b by dt. So this polarity, this minus sign, That is due to Ampere's circuital law, Biot-Savart law, Lenz's law, Fleming's left-hand rule. This one we today done this chapter. That's why it will come to your mind very fast. It is defined by Lenz's law because we just morning we done. But when it comes for the examination, all the chapters, so everything is mixed up. So you will have a doubt whether it is coming from which one. But we should know that the polarity is defined by Lenz's law. So I think you remember that one morning what we done so much in Lenz's law. But when it is asked in words, you should be clear about this one, because in this Ampere's circuital law or Fleming's left-hand rule, what is coming, you should know that one. Okay, this Fleming's left-hand rule and right-hand rule. So Fleming's left-hand rule is actually when we have a magnetic field and we have a current, a motion is produced. So this Fleming's left-hand rule gives the direction of motion when there is a current and magnetic field. And Fleming's right-hand rule is just opposite. That is, when you have a motion and when you have a magnetic field, it gives the direction of the current. Okay, so that also, when you are applying Fleming's left-hand rule and right-hand rule also, you should be careful, because it doesn't mean that what you have to find. Most of the children feels that Fleming's left-hand rule and right-hand rule is based on what you have to find. If you want to find the direction of motion, you have to use left-hand rule. If you want to find the direction of current, you have to use the right-hand rule, like that. It's not like that. It is based on what is produced. So if you are using the magnetic field and the electricity or the electric current to produce a motion, then you have to use Fleming's left-hand rule. And if you are using the magnetic field and motion to produce a current, so what is produced important. That is, if the current is produced, then you have to use the right-hand rule. You can just simply remember in the way in the case of motor, we are using left-hand rule, and in the case of generator, we are using right-hand rule. So motor produces a movement using current, and generator produces current using movement. So that way you can remember what is this one. Then Biot-Savart law and Ampere's circuital law also, you already done that one. Now we will go for another question. So this is also same type of simple question only. Lenz's law is a consequence of law of conservation of charge, mass, energy, momentum. Actually, this one was a topic which we are supposed to deal with the Lenz's law itself. Actually, morning session we not discuss that one. In morning session, if you take the topic, you once more you think about that one. We have a magnet. This side is north and this side is south, and we have a loop here. You are pushing this one toward this side, and when you push toward this side, here north pole is induced. This is what we discussed in the morning. That is, when you push the north pole toward this side is induced this north pole, and this is pushing it back. Actually, this is related with this conservation of energy. So I will explain how it is related with the conservation of energy. See here, for that one, we have to think in such a way that it is, if it is happening opposite, what will be the situation? That is, you have the magnet and you are pushing this magnet towards the loop. As per Lenz's law, you know that it is pushing back. If it is not pushing back, if the situation is opposite, when you push this north side toward that side, here north is not formed. For example, you think that here south is formed. If south is formed here, what will happen? Here we have a north and here we have south. When the north is pushed toward that side, this south will attract this north. So once it is attracted, this will get accelerated toward that side. So what is the meaning of that one? If you keep a magnet here and a coil there, once you slowly move that one, it will get attracted, it will go towards that side. So when it is going toward that side, we have an acceleration. So when it is accelerated, so we have the equation F is equal to ma, there should be some force. So here we are not applying any force. Without any force, it is getting accelerated, it is doing a work. That is against the law of conservation of energy. Clear? That is, if when you are pushing this one, if it is not opposing, if it is attracting, if it is not opposing, then it will violate the law of conservation of energy. That's why it should not be north, it should, it should not be south, it should be north, it should repel it back. So when it is repelling it back, then what is the meaning? When you are trying to push, it is pushing back. So that is in accordance with the law of conservation of energy. So this one can come like this, or it can come in another way. Directly they can ask, explain how Lenz's law is in accordance with the law of conservation of energy. Then you have to explain this one. That is, if you have a loop, you have a magnet, and if it is as per Lenz's law, what happens? It will get repelled. If it is not repelling, what will happen? Yeah, when you push, it will get attracted. Once it is attracted, this one is getting accelerated. So that is not possible. That's what you have to tell. It will not it accelerate without doing any work. That is against law of conservation of energy. That's why it should repel, or our Lenz's law should be in accordance with the law of conservation of energy. And you see here, this conservation of charge mass or momentum, that is not violated here. Okay, that is also conserved. Everything is right only. But this is a consequence of law of conservation of energy. That's all. It doesn't mean that these other conservation laws are not valid or something like that. Everything is, all conservation laws are everywhere. It is valid only. But this Lenz's law is a consequence of conservation of this energy, or conservation of energy. That's the thing about this question. Now we will move to another question. So this last question and this question was a very simple direct question. Now we will move to another question here. This one, actually you have to little bit you have to think in application level, but it's not that tough. Okay, simple only. But here we have to put the equation and try. That's all. See here, if the back EMF induced in a coil when a current changes from 1 ampere to 0 in 1 millisecond is 5 volt. The self-inductance of the coil is. So before going to the answer, first we will see what is given here. So the current is there. The current was 1 ampere first. This 1 ampere current goes to 0 ampere. That is, current is reducing from a maximum value to less value. So how much time it takes? So our current is maximum here. From here it is coming down. It is coming to 0 from 1 ampere. And it takes a time of how much? 1 millisecond. So 1 millisecond it takes. So milli means it will be 10 to the power minus 3. And 1 is millisecond is, and the induced EMF is 5 volt. That is, the EMF induced E is equal to 5 volt. So we have these many values. That is, from 1 ampere it is coming to 0. So the change will be this one, and the time required for that one is 10 to the power minus 3 seconds, and the EMF is 5 volt. So we have these many things. Based on this one, you have to find out what is the answer for this one. We will see that one how to do. So here you see, the EMF is given by minus L di by dt. This is the equation which we done in morning. What is di? Di means it is the change in current. So our equation, this EMF E is given by, that is 5. It is already given. This is 5. EMF is 5, which is equal to minus L. L is already given here. Then di by dt. What is di by dt? First you think about di. Don't think that always di by dt you have to take the derivative and all. It is same as delta I by delta t also. So our final value is 0, and the initial value was 1 ampere, and divided by dt, that is 10 to the power minus 3. So you will get it like this. So what is L here? L is equal to 5 into 10 to the power minus 3, and L is inductance. The unit will be H. So we have this option there as option C. In the previous question, you can see option C is this one, 5 into 10 to the power minus 3 Henry. So that is the answer for that one. Okay. So here, what are the things you have to take care is, this 5 Henry also is there. So when you are doing in a hurry, you may not take this millisecond. You may go directly to the second. So here 5 into 10 to the power 3 is there. So that problem should not come. Okay. That is. Okay, so this that you should take care. Okay. Now we will move to the next question. You see this question, question number 5. An iron cord solenoid has a self-inductance of 2.8 Henry. So the meaning is you have a solenoid like this, and inside this one we have iron. Just like an electromagnet, we have iron here, iron coiled, iron core actually. Okay, so this is inside this one is called as core. So we have a core there, iron core, and we have a solenoid here, and its self-inductance is 2.8 Henry. When the core is removed, the self-inductance becomes 2 millihenry. Here you see it was Henry, 2.8 H was there, and when the core was removed, it becomes very, very less. That is 2 millihenry. It becomes very less. So that's also one important thing. That is, when you have a coil, and inside the coil, when you have a core, the inductance is very high. And when you remove the core, only air is there, the inductance becomes very less. This is, even though it is a problem, you are getting an idea like that. When iron is inserted inside a coil, the inductance becomes very high. So from 2.8 Henry, it is reducing to 2 millihenry. Now the question is the relative permittivity of the material of the core. So you have to find out the relative permittivity of the material of this one. So what we can do in this one? See here, the situation is the L by L0. That is, this L is the inductance with the material, and L0 is without the material. So this ratio will be equal to 2.8, which is with the material, divided by this one. What is that? 2 into milli was there, 10 to the power minus 3. So this L by L0 will be equal to mu R for the relative permittivity. This mu R in the previous class we discussed. So mu R is equal to L by L0. So from this one you will get mu R is equal to 1400. You will get 1400. You will get here. So this 1400 is there as an option in that one. So you can see here this option A is the answer for this one. But this situation, this same thing you can do in our electrostatics, where we discussed about the capacitor also. If you have a capacitor like this, and if the capacitor is filled with a dielectric, and the capacitor is filled with a dielectric, with the dielectric constant K, here also the same situation comes. With this one we have a capacitance, and without this one you have a capacitance. This ratio will be same as the dielectric constant. This dielectric constant means it is actually epsilon R. I think you might have studied that one in the previous classes. That is epsilon R or this K, both are same only. So you will get like this in the case of capacitor. Not only this one, in the case of force also the same thing. You have force between two charges, and the ratio of the force will be based on the epsilon R value only. You have two charges kept here. One charge is kept here, another charge is kept here. In between vacuum is there, and we have a force between these two charges. If plus charge is here, minus charge, or plus and plus, whatever. And we have a force between these two. Similarly, if you fill this area with a material of epsilon R, then we have another force. So the ratio of that two force will be the ratio of the epsilon. So ratio of epsilon is relative. Epsilon, this epsilon R you will get. So the same question you will get an idea about three things. That is, one is about coil. When you insert a core inside that one, the value of L will be changing according to the ratio of this mu R. And in the case of capacitor also same thing. And for the force also same thing. You can use the same logic. I think this is clear. So the option A was right. Option A, this value was there in the previous slide we see. So this is also another question. So you see here, if you have the logical idea about that, even solving these questions are very simple. But the thing is, you have to see these questions once. Then the next similar question, whatever comes, you can solve. So you have to practice more questions like this. Okay. So one more question. We will go for another question. An inductor and a bulb are connected in series. This question can be considered as a question in AC or it can be considered as a question EMI. In both EMI and AC, this can come. An inductor and a bulb are connected in series with a DC source. So you see here, you have a inductor and we have a bulb. So this is a bulb and this is an inductor. Both are connected to a DC source. Okay, so it is connected in series with a DC source. So this is the situation. An inductor and a bulb is connected with a DC source. A soft iron core is then inserted in the inductor. What will happen to the intensity of the bulb? So here we have a soft iron core. So this is a soft iron core and you are inserting the soft iron core inside this one. So what will happen to the intensity of the bulb? That's the question. This is a question which is asked from so many years. So a little bit changes can come, but the basic concept is this one only. So what we discuss here, you know that when there is a coil, there will be a change in this one. But here one problem is there. This is DC. When DC is given here, what will happen? It will not have any effect. Electromagnetic induction we discussed. When the current is passing through this one, we will have a resistance for this coil. So this bulb will have a particular brightness because of the resistance of the coil. So that's about DC. So when you insert this one inside, what will happen? As this one is DC, there will not be any change. That point is very important because when you put this one, the inductance changes. That inductance cannot do anything with the DC. Because DC depends on the resistance actually. Because when there is a variation, then only all this inductance and such things will come into action. So when you insert this one, the intensity of the bulb remains same. This is the answer. The intensity of the bulb remains same because this is DC. Okay, soft iron got inserted in the, what will happen to the intensity of the bulb? So here, that's very important. As this is DC, it will remain same. Now you see here, instead of DC, if it is AC, if this question, same question comes with the AC here, then what will happen? AC means what happened? The figure I have to redraw. You have an inductor here, and after inductor, we have a bulb here, and this bulb is glowing, and we have a AC source here. So when you have a AC source here, these two situation is different. This is a time varying source. As the source is AC, when you insert a material inside this one, what will happen? The inductance changes. Inductance changes means inductance increases. So when inductance increases, the induced EMF also increases. Induced EMF means the back EMF. So already we are applying a thing, and the back EMF increases. When the back EMF increases, what happens? It is actually something like an opposition. So the brightness will reduce. Okay, so when such question comes, you should first check whether it is AC or DC, because you already studied for AC. When a inductor you are putting the brightness reduce, so that is already there in your mind. So this question will make a confusion, and this is given for making confusion only. Just like 10th standard, you have question in resistance. That is, you have a wire. When the length of the wire is doubled and the area of the wire is made half, what will happen to its resistivity? So most of the people will check when the length becomes double, the resistance becomes double, and when the area is double, it becomes half. But all these things are about resistance. The question may be about resistivity. Okay, so many times, even for 12th standard also, this previously such 1 mark question came. When a wire of length, something like 1 meter is taken, or the length is not given, and it is melted and made a new wire of a particular length, or the 10% of the length is increased. 10%, if so 10% increases means previous length L means it will become now 1.1 L. That is 10% increase. So when it is increased n times, its resistance will change with the n square times. That you might have studied in current electricity. If you have a wire and if you are extending that one to a 2 times means it will become 4 times. If it is 10%, 5% means you think what is the next value, that much square it will come. But the thing is, many times when it is, especially it's a 1 mark question and all, they may ask about the resistivity also. So that should come in your mind. The resistivity remains constant, only resistance changes. Same way, this one also. If it is DC, the answer is different. If it is AC, the answer is different. So you have to check in the question, and if it is given in the picture also, you have to check which type of source it is. So I think that's clear. So if it is the source is DC, this is the answer. If it is AC, what happens? The intensity of the bulb decreases. Okay. Now, when is there any chance for this intensity of the bulb to increase? Any other situation where it can increase? That's also one more situation. Actually, that you will discuss when you discuss the different materials, diamagnetic material, paramagnetic material, and all. When the diamagnetic materials are inserted, just like bismuth, there is a chance for increasing also. That we are not discussing now because it will make confusion. You should know what material it is according to the time. Once if you are doing the magnetic properties of the material, we will discuss. So generally, iron and that ferromagnetic material, when you are inserting, the brightness will reduce only. Now we'll move to the next question. So now we are going to the assertion and reason type question. So before going to the assertion and reason type question, you should know how to answer this one. So what are the options given in that one? In assertion and reason, we have option A, B, C, and D. So you see here, this is not same in every question. If you take this even the 10th standard and 12th standard question, it may be different. See here what is given. A, both A and R are true. That is, A is true and reason also true, and R is the correct explanation of A. That is, this is the correct explanation. That also is there. In the next case, you see, B, both A and R are true, but R, that is, assertion is true, reason also is true, but this reason cannot explain the assertion. So in your case, such questions you can get more. Okay, for that is that 2 cases are more actually. For assertion, reason, first you check whether the assertion is correct, statement is correct. Then you check the reason is correct or not. If both are correct, then if anyone is wrong, you see here assertion is true and the reason is false, and this is assertion is false and the reason is true. Actually, we don't have a choice here where both assertion and reason is wrong also. In this sample, it is not given, but you can check. Sometimes that also can come. So here, this first one, assertion is right and reason is right, and this reason should explain the assertion. So that's also because this one you should check whether this reason and mostly what happens when assertion is right, reason is right, people will write the first option. But you should check whether this assertion and reason or this reason explains the assertion or it is related with the assertion. Both are true, but it should have a relation also. And here the third option you see, A is true, but R is false. And the next option is A is false and the R is true. Like that also you can. So you'll go for 1 or 2 example questions for that. So here you see assertion A. What is assertion here? If the number of turns of a coil is increased, it becomes more difficult to push a bar magnet towards the coil. That is, you have a coil like this and you have a bar magnet. So when you are pushing the bar magnet, it will have, using Lenz's law, it will oppose. So it is difficult. So what it is telling is, if you have more number of turns, if you increase the number of turns, it will become more difficult to push. So that assertion will be right. Because when you push that one, if more number of turns is there, means the force will be more and it will be more difficult to push. That is correct only. The next one is the difficulty faced is according to Lenz's law. That's also right. because we already told it is due to the Lenz law only. So the difficulty is faced due to the Lenz's law. So you'll see here, both assertion and reason are right, and R is the correct explanation of A, because first when we started explaining itself, I told the same thing. So that is the correct explanation. So you should check whether assertion is true, reason is true, and whether it is the correct explanation. That also you have to check, because assertion, reason, question is something which you feel as easy and where the people are missing the marks. That's why you have to logically think. First you check whether assertion is right. Then if assertion is right, you check whether the reason is right, and next thing to check is whether the reason explains the assertion. Now we'll move to the next one. See here, this is assertion. When two identical loops of copper and aluminium are rotated with the same speed in the same magnetic field, the induced EMF will be same. That is, you have one loop which is made up of copper, another loop which is made up of aluminium. And identical loop, identical means their radius will be same, their thickness will be same, everything will be same. But one is made up of copper, another is made up of aluminium. And they are rotating in a magnetic field. So when this is rotating in a magnetic field, when two identical loops of copper and aluminium are rotated with the same speed in the same magnetic field, the induced EMF will be same. So you see here, our induced EMF E will be minus d phi by dt. So here nothing comes related to the material. So whether it is aluminium or it is copper, whatever is there, we are discussing only about the flux. Flux depends on the area only. So here, what is the material? That doesn't make any difference. So if you have any material, then the induced EMF will be same, because up to now we never discussed a copper wire or aluminium wire makes any difference. So this part will be true. Assertion will be true. Next one is reason. The resistance of the two loops are equal. Whether this will be right. So you study 10th standard, copper and aluminium, they will have different resistivity. But you can make it of same resistance if their thickness is different, because according to the resistivity, we have to adjust the length or this one so that we can make the. But if they have same length and same, all other dimensions are same, then their resistance should be different, because their resistivity is different. So this part is wrong. Okay, so we'll see the answer. Don't think whether answer is given. Okay, here explanation is given. The induced EMF in the rotating loop in a magnetic field depends on the area of the loop. The induced EMF depends on the area of the loop, number of turns, speed of rotation. The induced EMF depends on the area of the loop, number of turns, speed of rotation, and the magnetic field strength. These many things are there in this one, because we have d phi b by dt. So in phi means it is b dot a. So in that one, magnetic field and area comes. And this dt means it, d by dt means it talks about the speed of the rotation. So that also is coming. And the magnetic field already we discussed. It does not depend on the material. It is not depending on the material. Just now we discussed. So when two identical loops of copper and aluminium are rotated with the same speed in the same magnetic field, the induced EMF will be same. That's correct. It is induced EMF is same. The assertion is true. That's what we discussed just now. Now the resistance of the two wire cannot be equal. So the point is, if you have a induced EMF in a loop, that is independent of the resistance. If the resistance is same or resistance is different. But where it will come important? If you have a loop like this, you are taking a magnet toward this side, or some induced current is coming in that one, where the resistance becomes important. When you calculate the current, the EMF is induced, but how much current is passing through that one, that is important. That current depends on the resistance. So when I tell that one, we have to discuss one more point in that one. In Lenz law, we discussed one thing. We have a north pole here, south pole here, and a loop here. You are pushing the loop toward that side. So it opposes. So it is according to the law of conservation of energy we discussed. So we are pushing it, and that is pushing backside. So what happens to this energy? We are using some energy to push towards that side. Correct? This one is pushing back. So if you are placing inside that one, we are pushing it so that we are spending some energy. So what happens to that energy? So if you think about that energy, there will be a current in this loop, and there is a natural resistance for that one. So how much energy you are spending to push that one, that will be converted into heat energy. So this loop will heat using our Joule's heating effect is an I square RT. So this will get heated. Okay, so when we are discussing about current, we discussed this one also, that there will be a current. That current depends on the resistance, but the induced EMF is independent of resistance. Okay, now we'll move to the next. Next question you see here, we have an assertion: self-induced inductance may be called as inertia of electricity. This also we are supposed to do this one as the question is coming along with the question again. Once more we have to explain, that's why I left that time. Self-inductance may be called as inertia of electricity. So whether this is right or not. So what is actually inertia means? You see here, you have a big stone. You think about 9th standard or 11th standard mechanics. You have a big stone. So you are trying to push that stone. So you studied mass is a measure of inertia. So why you are not able to push it? It is having high mass. So the mass is not allowing us to push. So or it is that inertia is actually opposing the natural tendency of an object to resist the change. That is to resist the change of the state. That is, if you are trying to move it, it will try to stay there. And if it is already staying, if you try to stop it, it will have a tendency to move. That's called as inertia. So what happens is, inertia is always opposing the change. So now you take the case of inductance. You have a coil like this. So if you are trying to increase the current in this coil, what this inductance will do? It will be, the induced EMF will be minus d phi by dt, or there is a minus sign. It is opposing that one. So actually what happens is, you have a induced EMF in this one. That induced EMF will be always opposite to the applied EMF. So you have a polarity or a sign for this one when you are applying a EMF to that one, and the induced EMF will be always opposing this one. So that's why it's called as back EMF. This self-inductance, there is a induced EMF. That EMF is also called as back EMF. When we discussed that one, we told that one also. So the back EMF is always in the opposite direction. So it is opposing, and it is having a property like inertia. So it is, when you are trying to increase, it will reduce. When you try to reduce, it will increase. So the function of inductance in electricity is same as the work done by our inertia in mechanics. So that is a point here in question we are discussing, but as a theory part also you should remember that one. The self-inductance plays the role of inertia in electricity. That is, in mechanics we have inertia, and in electricity we have the self-inductance. So this part is true. The reason is here, due to the self-inductance, opposing induced EMF is generated in the coil as a result of change in current or the magnetic flux linked with the coil. Once more you read it. Due to the self-inductance, opposing induced EMF is generated. Due to self-inductance, induced EMF is generated in a coil as a result of change in current. So this statement is correct only, but you see that one, the explanation here. The inertia is defined as the tendency of an object to resist the change of state in the motion. Induced EMF of the coil is changed by the change in current. Same thing what we discussed. The property, all those things are okay. Self-inductance, up to here everything is same only what we discussed. Now you see here, so assertion and reason both are true. but the reason cannot explain why it happens. So once more I am going back. So you see here, this is true. This is what I told. This is true. This is also true. See here, due to the self-inductance, whatever happens, everything is right. But this cannot explain why this one is happening. So this type of situation also will come. Both are true, but this reason cannot explain why this is happening. Okay, so this type you have to expect more. Okay, but the thing is, you cannot tell more probability of whether both will be right or both will be wrong and all, or anything can happen. But you should not rule out this chance also. That is, you have the correct assertion, correct reason, but the reason is not explaining the assertion. That chance you should not rule out. Okay, we will move to the next question. One more assertion. Lenz's law does not violate the principle of conservation of energy. So this just now we discussed. This is correct only. The induced EMF never opposes the change in the magnetic flux that causes the EMF. Once you see this one, what is the answer you see? The Lenz's law does not violate the principle of conservation of energy. That is correct only. This one also, induced EMF never opposes the change in the magnetic flux that caused it. So just when you read it casually, you will feel it as right. But here one thing is there. Induced EMF never opposes the change. Actually, induced EMF always opposes. Induced EMF always opposes the change. So here this never is there. That's why this is wrong. So you should be very much careful about this one while dealing this assertion and reason. You have 4 marks for this one. Okay, 4 marks out of 70 is it's a good percentage where you can get it easily just by concentrating on the questions. Okay, and this as in the case of CBSE and all, we cannot predict that whatever came previously, same question will come. Every year it will be new only. So you carefully, word by word, you have to read that one. And the concept will be in most of the cases, assertion, reason, the concept will be basic concept only. But the thing is, you have to concentrate on that one, that question, that's all. Now we will move to another question. This is something like a numerical question. I think it will be clear. If it is not clear also, no issues, I will read it. A 0.5 meter long solenoid, that is, we have a solenoid, its length is 0.5 meter of 10 turns per centimeter. So this N is 10 turns per centimeter. So you should be careful about this one. It's 10 turns per centimeter. Has an area of cross section of 1 centimeter square. You should know all these things are in centimeter. This is in meter. This is in centimeter. This is in centimeter square. Calculate the voltage induced across its ends if the current in the solenoid is changing from 1 ampere to 2 ampere. This is very important. From 1 ampere to 2 ampere in 0.1 seconds. So when such questions comes, the first thing what you have to check is the unit. This is 0.5 meter. That's okay. Here you see turns per centimeter. Here also centimeter square. Here it is ampere, ampere, no problem. Here second also no problem. So we will go for all these values and we'll see how to solve it. Already it is solved so that we can save the time. So solution, you see, first I told you this L is given as L is equal to 0.5 meter. So no need of changing this L. Now number of turns, 10 turns per centimeter. In 1 centimeter, 10 turn is there, means in 10 centimeter we have 100 turns. In 100 centimeter we have 1000 turns. So the N will be equal to 1000 per meter. Okay, N will be 1000 per meter. Meter raised to -1. So this is the place where you will make confusion because it is given in centimeter. That's also given in centimeter. You will do it in centimeter, but it will not work. So you have to do everything in SI unit. Only thing where you can do it in other unit is you may be knowing that when temperature difference comes, you can do in degrees Celsius. Remaining all you have to do in SI unit only. So, and area you see here, area is 1 centimeter square. So you see here 1 centimeter square is this things and all should be careful. It is 1 centimeter square is 10 to the power minus 4 meter square. So centimeter to meter, when you are doing just 100 difference only coming, but when you are changing centimeter square, it is 10 to the power minus 4. If it is millimeter square, it is 10 to the power minus 6. Should not have confusion in that one. So it is 1 centimeter square is 10 to the power minus 4 meter square. And DI means what is that? DI means the final and the initial current difference, the 2 ampere to 1 ampere. So that will be the difference will be equal to 1 ampere. So from 2 ampere, it is coming to 1 ampere. So that is, the difference is 1 ampere. And DT, that is 0.1 seconds. Now all the values we first converted into SI units. This is what you have to do first. So length was already there. Number of turns was 10 turns per centimeter. We made it into 1000 turns per meter, and 1 centimeter square we made 10 to the power minus 4. And this DI means it is a change in current, that is 2 ampere to 1 ampere. So the difference will be 1 ampere. DT means the time taken, that is given as 0.1 second. That two are given in the question itself. You see here 1 ampere to 2 ampere, and that is final minus initial 2 minus 1 we taken, and it is in 0.1 second. That's also mentioned there. Now, the induced voltage, this E or V, whatever, that is given by V is equal to L di by dt. Okay. So whether it is minus or plus doesn't make anything. We want to find out the induced voltage. That's all. If plus comes, minus comes, the difference is the polarity. That side will become positive. This side will become positive. That's all. So this is L di by dt. Then what is L? For self-inductance, mu naught N square A into L, where length of this one. So these values we have to substitute into di by dt. So we'll just substitute from here. Very simple. So first one is mu naught. Mu naught. How to get mu naught? See here, it will be there in the question paper. First general instruction will be there. Below that one, the values can be there in the CBSE question paper. Otherwise, also you know this mu naught by 4 pi is the value is 10 to the power 7, like minus 7. So you can get it from there. Okay, you rearrange from there and you will get the mu naught value as 4 pi into 10 to the power minus 7 into N square. So N is 1000 here. So you have to take 1000 square here. Then what's coming next? Our area, that's also calculated here, 10 to the power minus 4. And after that, length 0.5, that's also here. Then next one is di by dt. So di is 1 here and dt is 0.1 second. So all the values are there. Just you do the calculation. So you will get like this. So this is 6.28 into 10 to the power minus 4 volt. Or you can write it as, generally we will write volt, millivolt like that. So you can take it as 0.628 millivolt. You can stop here. Somebody's mic is on. Once you switch off that. Mute your mic. Somebody's mic is on. Okay. So this is a final answer. Okay, so we have the final answer 0.628 millivolt. So we done a numerical problem here. This is not a big numerical problem. Just we explained here to say that how to deal it. You have to convert all these units and do like that. Okay. So similar questions also you can do. In most of the questions in EMI, this thing only is coming. This di by dt you have to substitute. That only when next question comes also you will see, or when you practice you will get most of the questions. Main thing will be this one only. This di by dt you have to do. Now we'll go for another question. See here, the mutual inductance of two coaxial coil is 2 Henry. That is, you have coaxial cables, coaxial coils. So you have one coil like this. And what is the meaning of coaxial? We have one axis like this. And the next is also above that one like this. So we have two coaxial coils. So this is one coil, and above that one we have another one. And their mutual inductance is 2 Henry. So the mutual inductance M is 2H. 2H means 2 Henry. the current in one coil is changed uniformly from 0 to 0.5 ampere in 100 milliseconds. So what is our change? 0 to 0.5. So 0.5 ampere is the change in the current. And the time is dt or delta t will be equal to 100 milliseconds. Find the change in the magnetic flux. This is a simple question only actually. Change in the magnetic flux through the other coil and EMF induced in the other coil during the change. So here also, just like the previous one we done, this is also something direct. You see the solution, this d phi is equal to m into di. So this m value already it is there 2 and change in current is 0.5. So you will get it as 1. So this is flux. The unit of flux is Weber. WB is Weber. So you will get it as 1 Weber. Now the second part is EMF. So EMF is given by E is equal to minus m into di by dt. Okay, so the induced EMF, m again the same value 2 into di by dt. Di means a change, that is 0.5. Minus 0 is there, means the same. And now you see here, our time, how much it was? 100 millisecond. Don't forget it. It is 100 millisecond. So it will be 100 into 10 to the power minus 3. When you calculate this one, you will get it as 10 volt. So both we got. Okay, this questions and all actually this is previously came for the examination. Okay, so you cannot take it as a silly question. These type questions also can come. Okay, so this is another question. So these all questions are of actually EMF. I told you now in the case of this electromagnetic induction, the main type of question is one is about the Lenz's law, what we done we done in the morning session also, when you are taking the loop out, loop inside, what happens? So that type of question. And second one is this type. You see this one. Current in a circuit falls from same way 0.5 to 0 in 0.1 second. That is this 5 ampere to 0. So it will, the difference will be 5 ampere in 0.1 second. If an average EMF of 200 volt is induced, give an estimate of the self-inductance. Directly, just you have to directly apply the equations for this one. This is the equation. EMF induced is minus L di by dt. So what is L here? L is already given. Sorry, L we have to calculate. This I2 minus I1 is I2 minus I1 is the change. So I2 finally it is 0 and the initially it was 5 and t was 0.1 second. Same thing is kept there. And L is here, the voltage is 200, that's also given there. Then you just rearrange that one. So you will get L as 4 Henry. It's a direct question, just you have to use this one. All the 3-4 questions what we done is almost same only. Same, similar type only, minor difference is there, that's all. Now, this one also same only. You can do yourself, that's all. A pair of adjacent coils of mutual inductance 0.5 Henry. If the current in one coil changes from 0 to 2 ampere in 0.1 second, what is the change in flux linked with the other coil? No need of any explanation, I think. Same thing, same calculation, same thing. The answer you are getting another. So this thing, why I am giving the same question means this is different years question. So the meaning is the same type questions are coming many times. Only minor difference is there. Now we will go for another question. Okay, this is also a previous year question only. The current flowing in the 2 coils of self-inductance L1, that is you have 2 coils, one with the L1 is 16 millihenry and L2 is 12 millihenry. are increasing in the same rate. That is very, very important. See, this is not telling about any current or something. This is telling about the current flowing in the two coil. It is the rate actually increasing in the same rate. That is, the rate of change is same, not the current. We are not telling the current is same. We are telling the change, rate of change is same, increasing in the same rate. If the power supplied to the coil are equal, so that is also important. The rate of change of current also same and the power is also same. So power is actually V into I, that's also same. In the two coils are same, that is given. Find the ratio of induced voltage, the currents and the energy stored. So this we have to do it as three parts. That is, first you have to find what is the ratio of the induced voltage, then you have to find what is the ratio of the current, and then you have to find the ratio of the energy stored. So you don't think everything as a single question. It's a different part. This first part will have an equation and you have to solve it. For that one 1 mark distribution. If it's a 3 mark question, 1 mark will be for that one. This is another part and this one is another part. So you'll see the solution of this one. So we'll go here. First we'll think about the induced voltage here. So how to get the induced voltage here? Same only, V is equal to L di by dt. That minus sign is not given, no problem. Okay, L di by dt. Now see here, we are not exactly finding out the value of this one because the question was to find the ratio. So we have to find out the ratio only, no need of finding out the exact value of that one. So how you will get di by dt? So V is equal to L into d. So you have two. So V1 and V2 is there. So V1 will be L1 into di by dt and V2 will be equal to L2 into di by dt. Now you have to get the ratio. So you divide it. And already in the matter it is given di by dt is same. So this one and this one can be cancelled. Then it's very simple. V1 by V2 is equal to L1 by L2. That's given here. V1 by V2 is equal to L1 by L2. So the value is given already 16 by 12. It will be 4 by 3. That's all. So this first one, directly by taking the equations and dividing, you will get it. Now we'll think about the power. Now power also is same. It's given. So power is P is equal to V into I. This is same. So what we can write? V1 I1 is equal to V2 I2. So now what we have to find? I1 by I2. I1 divided by I2 will be equal to V2 by V1. V1 by V2 we already got 4 by 3. So V2 by V1 will be 3 by 4. So we got that part also. So we got the first part and we got the second part also. So one answer is this one 4 by 3. Another answer is 3 by 4. So we are getting it very directly. We are getting just we are taking the value and dividing. So this type dividing and taking ratio, many places it will come when it comes to the optics. There also, when you are dipping a lens in the water and on such question also we have to do like this. We just have to take the ratio by dividing. So many values will be, you can cancel many values. Now, this part here also something is there. That is the energy stored. Same thing only, half Li square is there. You put the values of half Li square here because I value already given there. I1, I2. So the ratio half L square, Li square is there. So that value you put there. So you'll get it as 3 by 4 again because everything is direct substitution only. L is already given here. Then I also is given. The ratio of I is given. When you same way you write this one half L1 I1 square divided by half L2 I2 square. Then you do that one. So you will get I1 by I2. Already we have the value of I1 by I2 that you put substitute and you will get it. So this is another question, but this was a little bit different from the previous question. Comparing with that one, this is another question. But I already told you this is also a board question. Previously, this question also came for the board. And this one is actually a question which is a little bit different. But this one also in theory part we discussed, morning we discussed this one also. So we'll see here. I think this is the last question in this part. A rectangular, a square, yes. So this is different. A rectangular, a square, a circular, and elliptical loop. So we have different loops. One is rectangle, another one is square, and another one is circle, and another one is elliptical. So we have different types of loop, all in the XY plane. All are in the same plane, moving out from a uniform magnetic field with constant velocity. So it is in the XY plane. So XY plane will take like this. Let this be X, this be Y. So these things all are, if it is a square, it will be like this. In the XY plane only it is there. And it is moving in the V is equal to VI. So it is moving upward. This direction only it is moving. Okay. In the magnetic field, which is magnetic field is this directed towards Z axis. That's also given. So it is going perpendicular to this magnetic field only. So there should be a induced EMF when it is moving like that. The induced EMF during the passage of the loop out of the field. So it is not moving in the uniform field. It is moving from a higher field to outside. It is moving. Will not remain constant. So this will not remain constant for which one? Will not remain, that you have to see. So here you see the problem with that one is we will face from the front side and do that one. Any of the for loops. So the thing is, see, you have the field like this. So what is our induced EMF? E is equal to d phi by dt. Minus is there. Okay. So if you have a square like this, once the square or rectangle is going out, you see here, in 1 second, this much goes outside. The next second or millisecond, whatever is there, the same rate it is going out. So what happens? The induced EMF is proportional to d phi by dt. That is how much flux it is changing. So it is each fraction of time, the amount of this area going out is same only. Now, if you take the case of a circle, it is not like that. The first time it is this much is going. Second, it is going this much. Third, it is going. So what happens is the rate is different. So if you take these two, what happens? It is rate is same. For these two, the rate is not same. So will not remain constant for which one? The circular and elliptical loop, it will not remain constant. So this will be the answer for that. So that's how we have to check it. And one more, you have to check the direction of the magnetic field and all. If it is moving along the magnetic field and all, that will be different. So that's why they given V is equal to VI, like that it's given. So you have to check that one also, in which direction it moves, that also we have to check. So I think this is clear. So we are done with the normal type of questions which we can come from this part. And I told you that Lenz law type of questions also is required. So we will do that one also. Now we will move to that AC part we were discussing. So we will go to that AC. Okay, morning we done something about this one. Just once more you recall that one. We discussed about the alternating current. So it is varying like this. That's what we discussed. Now, this is the peak value. That the thing we discuss in the next screen, I think. Okay, here once more you see that is AC voltage applied to a resistor we discussed. So we have V is equal to Vm sin omega t and the RMS value and all we discussed. So when it is moving like this, we have the current and voltage. Current and voltage are in phase. And what is the RMS value? That also we discussed. That is we have a maximum value here and we have a RMS value also here. That much we discussed. Okay. Now, the same thing is given here. That is the I is the current. I is the current, which is the RMS value of that one. So that will be 0.707 times Im. That is Im by root 2. The RMS value will be Im by root 2. And in the case of voltage, V is equal to same thing, Vm by root 2. Okay, that is 0.707 Vm. So once more, let me tell you that this one in clear. That is, if you have a voltage like this one, this is called as the Vm, maximum voltage. And this one also is minus maximum here. So the voltage from here to here, the voltage from here to here, that is called as the peak to peak voltage. This one is called as the peak voltage or the maximum voltage. So when the technical term comes, you should be clear about that one. This is peak voltage. From here to here, it is peak to peak voltage. Now, the RMS value is the effective value of that one. That will come somewhere here. That is Vm by root 2. That is called as Vrms. Then why we are taking this RMS value means this AC which is moving like this, its effective value in DC is this one. Now we have a problem here. Actually, if our AC in our home circuit is, it is 230 volt or 220 volt. Okay, it varies from 220 to 230. So if it is a 230 volt or 220 volt, which is this 230, whether the top is 230 or from here to here the potential is 230, like that you will have a doubt. The actual thing is what we are measuring, that is 230. So the RMS value is 220 or 230. So what is the actual value? 220 into root 2. That is 1.41 into 220. It is coming nearly 310 volt. So our voltage will be 310 volt, going up and coming back to minus 310. So don't make confusion in this one. So any voltage which is mentioned will be our RMS voltage only. But it varies from a higher voltage to lower voltage. It goes up and down like this. Okay, so that's about our RMS voltage. So when AC is applied to the resistor, the voltage and current are in phase. That's what we discussed. And what is RMS voltage and RMS current we discussed. And this RMS value will be the equivalent of DC. That also we discussed. Now, the next thing is, when you study about AC, in resistor, we have the current and voltage are in phase. When you go for the inductor, capacitor and all, the current and the voltage are not in phase always. That can be out of phase also. So where it will be out of phase, that we will discuss now. Okay. And one more thing, how we can represent the phase. If you have current and voltage, they are out of phase or they have a phase difference, we have to represent that one, and we should understand what is this phase difference. So for that one, we have a particular way of drawing graph. That one we can draw it as a graph using the vector notation. That is, we are using the concept of graph and vector together. So for that is called as the phasor diagram. So now we'll study about the representation of AC current and voltage by rotating vectors. That rotating vectors is called as phasor. So how we can represent this AC using this concept of phasor? That's what we are going to discuss now. Okay, now this is a simple example given here. It's about the resistor only. So you see here, what we have is, we have a axis like this. So in this one, we have current and voltage. This is the current and voltage which is passing through a resistor. So our voltage is like this. So this is voltage V, and we have current. Current is in same phase. So there is no phase difference in this one. So you can see here, this is 0, and this value will be the maximum Vm, and this is I, and here it will be pi, and here it is pi by 2, and 2 pi, like that you will get the wave. Now, the same graph we can represent as a phasor diagram. So you see here, in phasor diagram, what we are doing is, we have a rotating vector. So you see here, this voltage we have to represent in this one. So for that one, what we will do is, you take a random time, because our voltage is given by V is equal to Vm sine omega t. So this sine omega t, this what at a particular time, what is omega t? If you take a particular time, you take omega t, you will get an angle. Let that angle be here. So this is our value of omega t. So what we have to do is, at this time, what is our value of V? So this is our value of V. So in this one also, we should get the same V. So what we will do is, this angle, this omega t, let it be 45 degree or whatever. So in that angle, we will draw a line, a vector like this. And its height will be the same, this one. So this angle will be omega t. Okay, if this angle is omega t, you know that this is the length of this one is V, and this is omega t. So what about this height? This height will be, this is Vm, the length can be Vm. So this height will be Vm sine omega t. So I think that's clear now. So you have a vector like this. The length of this one is Vm. So you see, initially at this point, when this omega t is 0, it is like this. Its height is 0. When it reaches to here at 90 degree, it turns up to here. So we have the full length, V is equal to Vm. In between, if you take any angle, that height we will get on this line. So when it turns this side, you see here afterwards it comes down. So this also will come down. And it comes here, and that is this point. Then again it goes like this. So what is the point in that one? If any value of omega t, if you draw a line toward this y-axis, you will get the value of V at that instant. So instead of moving it front like this one rotates. So that is our rotating vector. Now here, if you take the case of current, current is also in the same phase. So it will come here only. The graph will come here only. That also will rotate. So that's how we will draw a phasor. So now you'll feel it as simple here, but it will have a difference when you have different angles. So that situation also I will explain to you. See here, you think about two waves with a current and voltage with a phase difference. For example, your voltage is like this. Okay, and this becomes maximum here. This is starting a little bit late, like this. So this is V, this is I. Now the same concept is taken here. Our omega t, same point here only. Here only omega t. Now you see here, the V, where it will come? So here is our V. This is the length is Vm, and this total is V. Now you see here, this one started from here. So when voltage becomes maximum, that is, when this became 90 degree or pi by 2 angle, that time only our current starts from 0. Or always this current is behind with an angle of 90 degree. So the current is lagging behind, or the current is moving 90 degree behind. I think that's clear. So where you have to draw? You have to draw this one here. So this is our current. So the voltage is here and the current is here. and it is having a different space difference of 90 degree. That 90 degree you can see here. So when it is going front, when this is going front, this will rotate. When this reaches to here, this will be here. When this reaches here, this will be here. So it will rotate in such a way that always this will maintain an angle of 90 degree. So that's how we will do the or we will use the concept of rotating vector to represent the AC voltage and current. So this type of diagram is called as phasor diagram. So first when you are drawing this phasor diagram, it is better to draw this one and connect to this one. So when these both are together, it will be easy. Okay, so you make sure that you draw this one and like this you draw and then you will get a clear idea about that one, how to draw that one. So actually, when both are in phase, it will be in same direction. The real idea when you will get, then there is a phase difference only, because when you are studying inductor and capacitor current voltage and all, you will get that one because there is a phase difference in that cases. So we will move to that one also, inductor and capacitor, how it works. Okay. So first we will go for AC voltage applied to an inductor. When AC is applied to an inductor, how it is. That's what we have to discuss first. So here in this picture, you can see we have a circuit here like this. In this circuit, we have a AC source here. And from this AC source, the current is passing. The direction of current is not marked here because AC, the direction continuously changes. So that's why we are not marking the direction of current here. So here we have a coil or an inductor here. So L is marked here. Now we have to find out what is the voltage here and what is the current here, what is the angle between voltage and current. All those things are our work now. So in the beginning, what we can do is, first we will see what is the voltage here. Voltage produced by this one that you see here. In all the cases, we will take V as V is equal to Vm sin omega t. So that just for our easiness, we are taking V is equal to Vm sin omega t. With respect to that one, what is the current that you will find out? It can be opposite also, but we are doing, we have for a uniformity, we will do the voltage is like this, and with respect to that one, where is the current, we will check. So V is equal to Vm sin omega t is the voltage here. Now we will use Kirchhoff rule here. What is Kirchhoff rule? In the total loop, the total potential should be 0. That is, here we have a voltage which is V, this same V, minus we have a voltage across this inductor. Across the inductor, what is the voltage? That will be L di by dt. That we studied. The potential across the, or the EMF across the inductor will be L di by dt. So V minus L di by dt is equal to 0. Okay, so V minus L di by dt is equal to 0 we got. Now this one we can rearrange. How we can rearrange? Di by dt is equal to V by L. Now for this V, we will substitute from here. So what you will get? Vm sin omega t minus L. So what you got? Di by dt is equal to Vm sin omega t by L. So this is di by dt. We need the current. So what you have to do? You have to integrate this one. Integral di by dt is equal to this constant we will take outside, Vm by L integral sin omega t dt. You'll get like this. So this integral will be I. Integral di by dt will be I is equal to the same thing we will keep here, constant here, Vm by L, and integral of sin omega t dt. So what you will get? Integral of sin omega t dt will be cos omega t plus a constant, and you have to multiply because it is not cos t, it is cos omega t. So you have to divide it with 1 omega here, and a minus sign also will come. Minus Vm divided by omega L cos omega t plus C you will get. And you see here, what is this plus C? Plus C is a constant. In our AC case, see here, AC is like this. Okay. Then if you add a plus C, a plus constant, if you add, what happens is this entire thing will get lifted to this area. So there is no difference in the AC there. Only this graph will get lifted. That's why that constant is plus C, that constant is not relevant in the case of our AC or AC, because that is not making any difference there, because we are taking the change only. The entire graph gets lifted means that will not make any difference in the case of AC. That is only DC component. Now, this one, we will discuss that minus cos omega t part. Okay, here we have a minus sign. Okay, minus cos omega t. What to do? We'll see here. This minus cos omega t can be written as sin omega t minus pi by 2. That is minus cos omega t. So what we can write now? I is equal to Vm by omega L into sin omega t minus pi by 2. Now this Vm by omega L, that we will write it as Im. So I is equal to Im sin omega t minus pi by 2. Okay, so this is not the final thing. Still here we have some importance. So what was our voltage? V is equal to Vm sin omega t. And what is our current? I is equal to Im sin omega t minus pi by 2. So here we have one important concept here. That is, in the case of an inductor, what happens? The current is at an angle pi by 2 behind the voltage. So here this phasor diagram, you can see voltage is here, current is lagging behind by an angle of pi by 2. This one once more we will study in detail. That is how this the meaning of lagging and leading. So this in an inductor, the current is lagging behind by an angle of pi by 2, or we can say the voltage is leading behind in front, or leading by an angle of pi by 2. Or you should know that in the case of an inductor, the voltage and inductor have a phase difference of pi. And what is leading here? In an inductor, the voltage is leading. The voltage is leading and the current is lagging. You should not forget it. It's very, very, very important. Now, this part also I will take once more. This Im is given by Vm by omega L. Actually, the normal equation, what is current? Current is equal to voltage by resistance. So resistance is actually the opposition. So there is some opposition called resistance. Here in the place of resistance, what is coming? This omega L is coming. So we can write it as Im is equal to Vm divided by XL. What is this XL here? XL is actually XL is equal to omega L. This plays the role of resistance. And this is called as the reactance, inductive reactance. It's called as inductive reactance. So that is very, very important. When the current is passing through a particular resistor, we have resistance. That is applicable in the case of DC. In the case of AC, when AC is passing through a coil, just like resistance, we have another quantity which is called as the reactance. So reactance is also just like resistance, it's opposition only, unit, everything will come same. It is an opposition to AC. And you see here that reactance depends on the frequency also. So see here, XL is equal to omega L. That is, when the frequency increases, the opposition also increases. So XL is equal to omega L means this omega increases means XL also increases. So the meaning of that one is, when AC is trying to pass through a coil or an inductor, there is an opposition. This opposition increases with the frequency. So if it is very low frequency, DC or near DC, it can pass through the coil. So if it is AC, when AC is trying to pass through an inductor, it is blocking. So the inductor can block the AC or it can oppose the AC. It will allow the DC to pass through that one. Okay, some more in detail, this graph we will discuss later. Now we don't have time. So in the afternoon session, we will complete this one and we will do some problems on AC also. So for time being, we will wind up now and we will see in the next session, 6:30 session, we will see. Thank you.